So we will start on chapter 7 today, chapter 7. And it's not a long chapter. Some textbooks make it a little longer. And again, I have everything messed up here. Spring 2025. Okay, spring 2025. All right. Today, we will also do a statistical simulation in Python. Okay. And I feel like that's one of the, I think having computational tools in any classroom, in any course you take, having someone, or if your teacher knows, kind of has a little bit of knowledge on using computational tools to inject in the subject, I think that is useful. So if in your selection of courses, if you have a choice between different sections, obviously you want to pick the more effective teacher, but if they're both as effective, pick the one who might have a little bit more inclination to do computational stuff, because I think that's tremendously helpful. So we'll see what we're going to do today. It's going to be a fun exercise. We're going to prove the central limit theorem, or observe it at least. So at the end of this chapter, you will be able to explain the general concepts of estimating parameters of a population or a probability distribution, explain the important role of the normal distribution as a sampling distribution, understand the central limit theorem, perform a Python simulation of sampling from a distribution, and demonstrate the central limit theorem with Python simulations. Okay? So the first thing we want to talk about are what we call sampling distributions. And all the words in statistics, they get overwhelming. There's a lot of words that can mean different things, could be contradictory. So I'll try to remind you of those and remind myself as we go along. So a new word we will use today is called the sampling distribution, and we'll define that very, very carefully after we do this exercise. So we're going to do this experiment first. We're going to take a fair die, and we are going to roll it 300 times. Now this die has 6 faces. Right? It's a fair die, so it has equal probability, equal chance of landing on each side. So first time you get 1, 1, and then 3, 4, etc. Now record all of those experiments and make a histogram. Okay, this is our experiment. Gonna make a histogram. It's gonna look something like this because it's only 300 times. So you might get a little bit more of phase 1, slightly less than in phase 2, a little bit more in phase 3, but they're almost equal, right? So because there's an equal chance for getting each one, and there's 6 of them, so you'd expect about 50 in each bin. There's, 49 here, there's about 40 here, there's 55 here. That's okay. That's still approximately a uniform distribution of likelihood of landing. So we agree with this, right? We agree with this. This is what you would get if you roll the die and keep recording. So you roll it once, you record, okay, I got 1 on the first time, I got 2 on the second time, and you just count how many times you got 1, how many times you got 2, how many times you got 3, etc. That's the histogram, okay? It's a frequency. Okay. Now, I want to consider this as our population. The 300 times that we roll the die, forget everything else, this is our population, and the numbers in this population, so think of these recorded numbers as sheets in a bag, or as numbers in a bag. Okay, that bag is going to be our population. All right. Now, this population contains values of the die faces. For example, I'm not going to list 300 of those, but there might be, like I said, 49, number 1. There's about, 40 of number 2, 50 of number 3, and so on, right? So we agree with this. This is our population. It just contains die faces. Next, what I want to do is take random samples of this population. I'm going to close my eyes. I'm going to shake the bag very, very well, right? And I'm going to go in and grab 1, 2, like the lottery. Grab 1, 2, 3, 4, 5 samples, let's say, 5 faces from this one, okay? So just for the sake of the argument, I'm going to grab 5. That number is going to be important. How many you grab is going to be important. And I'm going to do this with replacement. So I'm going to take a number and then put it back. I'm going to take a number and then put it back. Take a number and put it back, okay? So that's with replacement, all right? Now, hint, hint, this is how we do most sampling. It's going to be random sampling with replacement, even sampling from a population of people, okay? But in this case, definitely with replacement. So I'm going to pick 5 faces from this bag, from this population, then put them back. Now, this 5 could be 50. You could pick 50 and put them back. You could pick 60. You know, there's billions of combinations how you can pick 5 faces out of this bag, okay? And I'm going to do this many times. So I'm going to do this once, that's sample 1, and then another time, and then another time, and so on and so forth. And every time I'm going to put everything back in the bag, okay? So this could be, for example, sample 1. This could be sample 2. This could be sample 3. They're different numbers because I'm just randomly sampling, shaking the bag every time. All right. Next, what I want to do is compute the mean of each sample, the mean value of each sample. Okay? We're going to compute the mean value of each sample. So in this case, for example, for this first sample, I have 2 plus 3 plus 5 plus 6 plus 6 over 5. It's a simple arithmetic mean. Okay? Just add the faces and divide by the number in the sample, so you get 4.4. In this case, we got 3.8. That's 1 plus 3 plus 4 plus 5 plus 6 over 5. And then in this case, 2 plus 2 plus 3 plus 4 plus 5 over 5. You got 3.2, and so on. You do that for all of those samples. You can do as many samples as you like. Okay? Now, obviously, and as we see from this even very little example, the samples will have different means. They're going to have different means, right? But what I'm more interested in, and what is going to be important for statistics, is asking how are they going to be different? In other words, how are the sample means going to be distributed? Are we going to get many sample means that are going to be 3.2? Or are we going to get more sample means that are going to be around 4.4? So I'm going to pick different samples, record the average. And we can define an interval. Let's say, sample means between 1 and 2, between 2 and 3. How many means are you going to get in each one of those bins? Do you know the answer? Let's try to guess together. Okay? I want to guess with you because we can intuitively guess what the distribution of the sample means is going to look like. So when I talk about the distribution of the sample means, on the x-axis, I'm putting the mean value of each sample. Or I'm going to put them in bins. Okay? So on the x-axis is going to be the value of the mean of each sample. The y-axis is going to be the count. Agreed? That's what it's going to look like. All right. So I want to intuitively figure this out with you. So on the x-axis, we're going to put the sample mean. On the y-axis, we're going to put the count. How many sample means did we get in this category? How many means did we get in that? And so on. So I'm going to bin it. So obviously, you're not going to get exactly 3.2 or 3.8 every time. You're going to get a range. So we're going to bin them. OK, now what is the range of my sample means? What's the smallest sample mean I could get? And what's the largest sample mean I can get? 1 to 6, exactly. The smallest sample mean is going to be when you reach out to the bag and pick 1, 1, 1, 1, 1, 5 ones. All right? That's going to be the smallest sample mean. That's by definition, that's because there's no smaller numbers in the bag, right? So your least sample mean is going to be 1. And your largest, okay, so we're going to draw that here. And your largest sample mean is going to be 6, okay? Because you're getting the largest number. What if you pick 6, 6, 6, 6, 6 from that bag? Divide by 5. So 5 6s divided by 5. That's going to give you 6. Okay, so I'm going to put 6 over here. Now for simplicity, I'm going to put the following bins from 1 to 2, from 2 to 3, from 3 to 4, 4 to 5, 5 to 6. Okay, those are going to be my sample means. So now, when I do these samples, I take a sample, I compute the mean. If the mean falls between 1 and 2, I'm going to register a number here. So because I'm counting, there's 1 here, and then there's 1, 1, 2, etc., etc. So now the question, how are those bars going to look like?
I would say between 3 and 4 will count the most. And depending on the size of the sample, they'll be distributed differently.
Okay. Finn?
I think Like, I think it's all going to be equal after.
So we have our population is 300.
Oh, 300. Okay, yeah.
Our population is fixed, that's 300. But the samples, we can draw an infinite number of samples. Okay?
If it's a fair dice, it should all be the same. Then.
They should all be the same count. Okay? Why would it be a bell curve? That's what I'm trying to.
Well, it's just because like the least probable thing is a 6 and a 1, and the most probable, like you said, is like between a 3 and 4.
Okay, so you're agreeing with Nicholas. Okay? So Finn has different opinion. Any more opinions? Okay. All right, let's think this through together. You said something very important, that what is the likelihood? So a mean between 1 and 2, when can I get that? Is when I sample 1, 1, 1, 1, 1, right? Or 1, 1, 1, 1, 2, or 1, 2, 1, 1, 1, 1, right? That has a very, very small chance of getting this sequence together, right? It's extremely unlikely that you would sample from the bag 1, 1, 1, 1, 1, 1, right? Or 1, 1, 1, 1, and 2. Because you have a sequence of numbers that are like identical, right? Versus if you go to the middle between 3 and 4, this could be 1 plus 4 plus 5 plus 6. There's more of those numbers in there. There's more of those combinations in the bag, right? Same thing happens on this side, because getting to 6, between 5 and 6, you're going to be sampling 5 plus 6, 6, 6, 6, 6, right? What are the chances of that happening? They're low. Even like common sense tells you that. Why? Because the bag is equally distributed across all of those numbers, right? But adding them is changing that probability. So the bag, there's equal likelihood for all of these numbers to exist equally. But to put them in this mean, you need a lot of 1s here. You need a lot of 6s here. Over here, it doesn't matter in this bin. In this bin, it's even less important. You could do 3 and 4 and 2. There's a lot of those numbers. So I will agree with Nicholas and the team there that in this bin, we're going to have the least probability or the least counts. In this bin is going to be a little bit better, and this bin is going to be the most. Just because, now the numbers in the bag, remember, they're equally distributed. There's an equal chance of picking 1 and 2 and 3 and 4, because that's a uniform distribution we started with. But when you add them together, when you take an operation on that random variable, it changes the likelihood, it changes the counts. All right? It is a bell curve, and I mentioned that earlier, that the means are all going to be looking like a bell curve. Okay? In fact, the theorem we're going to study today is that the sample means will always be normally distributed. Okay, so if you have a probability experiment or a statistical experiment that looks like this, you have a population, you're sampling from the population and then computing a mean, then those means will always be normally distributed. This is mind-blowing, because this is true for any type of statistical experiment that you will do, and regardless of how the original population is distributed. And we're going to demonstrate this in Python. So even if the die was not fair, you'll get the same bell curve. Whatever distribution the die or the population has, it does not matter. The sample means will always be normally distributed. This is insane. But yet it's so easy, because intuitively we kind of just figured that out, right? Now, if the die is not fair, it will still be a bell curve. It will just shift the mean a little bit, because there's more likelihood of getting one number versus the other. You're just shifting the mean. Okay? So we will demonstrate that with Python together. Okay? This is going to be next. Now, before we hit that in Python, we're going to need a few things. I know we're focusing on SciPy with probability distributions. We're going to stick with SciPy with probability distributions. But in this case, we're going to need some arrays, and we need to manipulate some arrays. And what library is best at manipulating arrays? It's NumPy, the NumPy library. And we will need the following few things from NumPy. We're going to need numpy.random.randint So that is going to generate random integers uniformly distributed. Why? Because I'm not going to have you roll a die 300 times and record the thing. It's going to take us an hour. So I'm going to simulate that experiment of rolling the die 300 times with NumPy. And we're going to use randint, and we're going to generate a random integer between 1 and 6 300 times. And there's an equal chance that each one of those numbers is going to occur. Does a good job at doing that. The next one we're going to use is NumPy random.choice. Choice is going to allow us to sample from those 300 generated numbers, or choose. I wish they called it sample, but you're choosing from an array. Okay. Now, NumPy.random.choice is going to be very powerful because you can also assign probabilities to it. We will do that when we do an unfair die. So we'll keep that in mind. And then for each sample, we need to compute the mean value. Agreed? Because we just did that. That's the experiment we're trying to reproduce. And I need to plot a histogram to count, to do the counts. Okay, so we need a plt.histogram. All right, let's get our Jupyter notebooks, and we can run this statistical simulation. I feel so sophisticated when I say that. It's a statistical simulation. Now, when you get to data science, my hope is, this course will evolve to become more data science centric. This is the stuff you will be doing. You'll be doing random samples. You'll be choosing from samples. You'll be when you train a neural network, you're running over different samples and you're training the neural network. So this is the stuff of AI, okay? It's not as sophisticated because we're still taking baby steps and understanding probability and statistics, but it's one step in that direction, okay? All right, so what we will do, we're going to create a new, what is scary? Okay, come on, create a new notebook for me. Pop-up window blocked. What the heck? Oh, okay. All right, so we're doing a Python kernel, and I'm going to call this in class simulation of fair die and sample means. Okay. Again, I am not going to document what I'm doing. Apologize for that. I don't have the time to do it. You should. You should explain what you're doing. You should put text of what you're doing. Okay, but here in class, please excuse me for not doing that because it will take up all our time. Okay. All right. So the boilerplate we will need in this case is going to be NumPy, obviously. So import NumPy as NP, and I am going to import matplotlib. Import. You can copy this from the previous one we did. You can just copy this from here and just put it here, actually. Maybe if you don't have that notebook open, take a moment to copy it. Okay, so step one, generate 300 rolls from a fair die, so 1 to 6. Okay, this will be our population. So what we're going to do, we're going to just generate random numbers with equal likelihood that each number is going to occur. Okay, and we're going to put them in a bag, in an array. That's our bag, that's our population. Okay. So how many die rolls we're doing? Die rolls is equal 300, all right? Or, hold on, let's call it n rolls. N rolls or total rolls is equal to 300. So total number of rolls. And then our population, or die rolls, is going to be equal. That's what I'm going to use at numpy.random.int. So I already gave a nickname for NumPy. It's np.random. Random is a huge module in NumPy that does random stuff. It's a random number generator. And from it, I need to generate random integers. Now, NumPy is well documented. This tells you it returns random integers from low to high, inclusive, okay? Low inclusive to high exclusive. And it returns random integers from the discrete uniform distribution. So there's equal probability of the specified type, half open interval, and uniform. So what's important here is to recognize that these numbers are going to be uniformly distributed. There's an equal chance that each one of them is going to occur. How do you get that probability? It's 1 over the largest number that you're getting, 1 over 6. If you put from 1 to 10, it's going to be 1 over 10, and so on. Okay? So I'm going to go from low, I want 1. High, I'm going to put 7 because it's exclusive. So if I do this, it's going to generate numbers from 1 to 6. Okay? And then next, I'm going to generate how many of these numbers? Size is equal total rows. Okay? And I run it, and it runs great. Now, what does die roles include? If you're in doubt, print it out. You print die roles. Okay? It's just a bunch. It's a bag of numbers that contains the die faces, right? It's an array containing the die faces. On the first roll, we got a 6. Second roll, we got a 3. Third roll, we got a 4, etc. Now, I claim that these numbers are going to be uniformly distributed. So if I plot a histogram of these, and each bin I count, you know, how many ones I got, how many twos, and so on, it's going to be approximately flat. It's going to be some variation because I'm only doing 300 rolls, but it's going to be a good approximation. So to do this, I'm going to do a histogram. So next, we're going to plot and verify our distribution of die faces. Okay, that. Okay. So I'm going to do plt.hist. What's nice about the histogram function in Python, it allows you to also do it as a density distribution. So it converts it to a probability instead of count. It's not bad. Okay, so we're going to plot. Now, when you put the histogram, you're going to give it the array that you're looking at and the bins. That's what's going to be important. Now, the bins is going to be an integer or a sequence of floats or strings if you have categories. I'm interested here in a numbers. So from 1 to 2, 2 to 3, 3 to 4, and so on. And what does that mean? What are those bins? Are those bins the left edges, the center edges, or what? So if I give it a sequence, if bins is a sequence, it defines the bin edges. So I want my bins to be 1, 2. So it gives me the first bin. 2 to 3, 3 to 4, 4 to 5, 5 to 6. Right? Those are the bins that I want. Right? If bins is a sequence, it defines the bin edges, including the left edge of the first bin and the right edge of the last bin. In this case, bins may be unequally spaced or whatever you want. Right? Okay. So let's go ahead and try this. Go ahead and try this. Okay, let's see. So I'm going to do die roll. So that's my population. Agreed? That's my population. And let's experiment with bins. You can put a sequence. So we're going to put 1 to 2. And then, so that is going to be centered at 1. Right, so let's see, 1 to 2, 2 to 3, 3 to 4, 4 to 5, 5 to 6. Let's see what it does. Okay, that's not quite what I want, because I want them centered at 1. So I'm going to add one more number here. So if I add one more here, and let's see if I add one more here. Actually, no, let me do it this way. I'm going to do from 0.5 to 1.5. Okay, that's not quite what I want. I want to move the bins. I want to move the bins half a point so that they're centered on the face value. Okay? So here's how I'm going to do this. I need to subtract 0.5 from all of these. But I cannot subtract from a list. It's going to give me an error, right? So it's going to throw an error. So I need to convert this to a NumPy array and then subtract 0.5 from it. Ta-da! Good stuff, Professor Saad. Like we did in numerical methods, you just put the NumPy array put the list in the NumPy array. So for those who are just doing Python in 1703, you just define the NumPy array with that list. We've done this numerous times in numerical methods as well. Now, okay, this is approximately uniformly distributed. It's not exact because we only have 300 samples. So if I do like 3,000 samples, 3,000 times is going to be more and more uniformly distributed, okay? Because we're reaching the true law of like large numbers with uniform distribution and random number generation. But I'm going to stay with 300 total rows, okay? And notice every time you run this, it's going to give you a different plot. So don't freak out if you get something different than mine. The random number generator is going to be based on your internal computer clock to seed the random number generator. Your hardware is going to be different. So you're going to get a different looking plot. But as long as it approximates that, you know, we have about the same amount in each one of those bins, then we're good. So what does this histogram mean? What does it mean? What does this bin mean? Means phase 1, we have about 40 phase 1 value in that bag, in that array. So if you take that array, count how many ones we have, this is how much. Count how many 2s, how many 3s, and so on. Okay? Perfect. All right, so what are we going to do next? Now, obviously, you want to add labels and stuff, so don't do my, don't be foolish like I'm doing here. Just kind of be, just put labels and make sure you explain what your axes are. Okay, so I'm giving a bad example here because I don't have time. Okay. Now, it's going to be interesting. Step 3, okay, so that's step 1. I guess this is step 2. Okay, plot this. All right. Step 3, right? Now, whoops, step 3 does nothing apparently. Okay, step 3. Now we're going to take some samples, take a bunch of samples from this population. Let the sample sizes be 30. Okay. I did in the slides, I did 5 size of the sample because, you know, I didn't have room in the animation. It would have taken me a day just to kind of animate that. But in reality, and as we will see, we will need a lot of samples to prove this bell curve. We will need a lot of samples, and the sample sizes have to have a minimum size. All right, so I'm going to start with 30 sample size, and we can do a lot of samples. So we'll start with a few samples. Right, so I need 2 things. Num samples, number of samples, and that's equal, you know, let's start with 10 samples. Now, how many samples can I draw from a bag of 300 numbers, and how many samples of size 10, let's say, or size 30 with replacement? Very, 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 it's a Googleplex. It's like, oh, it's a very large number, okay? It's a very large number, okay? Because order doesn't matter, so it's a very large number. So I can draw an infinite number of samples by all reasonable standards. And then the sample size is going to be 30. So I'm drawing 10 samples. Each sample has 30 numbers in it with replacement. Okay, so I'm draw the number that I replace. I might draw it again. Okay, all right. So now I need to build my samples and my sample means. I'm going to do this in one line of code, but before I do it with one line of code, I'm going to build it with you one step at a time. Okay. So how do I draw a sample? Draw a single sample. Sample is equal. This is where numpy.random.choice comes in. Now, choice generates a random sample from a given 1D array. Couldn't even be clearer. So this is exactly the routine that I want from Python. So I'm going to give it a 1D array, and I'm going to ask it to draw a random sample from that 1D array with a given size. Okay? Pretty neat. It has some really cool features here. So you require the array and size. Replacement, you could replace it. So exactly what we're talking about. So these people have taken this course apparently. And then P is the probability of choosing one number over the other. Okay? We will get to that with the unfair die, but in this case, we have equal likelihood of choosing any one of those numbers. Okay, so we're not worried about P over here. Okay, so if I do numpy.random choice, okay, and what I want is from my die rolls, I want to select samples from my population, which is die rolls, and size of my sample is sample size, right? And replace with replacement equal true. Okay, so that gives me one sample. Okay, for simplicity, I'm going to comment this plot so I can focus on. Actually, let's go down. Let's go down here. Let's go below this plot so we can focus just on this. All right. So what does sample contain? Print sample. Always ask yourself, what am I doing? Like step by step, right? What does my sample contain? It contains what? 30 numbers that have been randomly selected from my population of die rolls with replacement. So pick a number, replace, pick a number, replace, pick a number. 30 of them. Equal likelihood, everything is being picked. I'm not biasing any part of the bag, the bottom or the top, the middle. Okay, like pure lottery. Okay, that's great. Now to get to the answer of the simulation, remember the question I asked you: how are the means of the samples distributed? Right, that was the question. So what we're doing here in Python, we're going to generate these samples. We're going to take their means and we're going to plot the means to see how they're distributed. Right, that's what we're after. Now the population, we already simulated that with random int. Now we're focused on the samples. The next step is to get the sample mean. Okay, so sample mean is equal. What's the other function we talked about in the slides? Was mp.mean. What does numpy.mean do? It computes the arithmetic mean of an array along the specified axis. Just returns the average of the array elements. So in other words, what I want is np.mean of sample, right? And I can print that, print sample mean. Now this is going to return a what? Sample mean. Pritten. Yes. All right. Now if I run this again, it's going to give me a different number. Why? Because this is a random numbers thing, right? So I'm going to run it again. It's going to give, well, no, the sample has been selected, sorry. So if I run this again, it's going to give me a different, might give me a different number. Look at that, it's 4. Now it's 3.633 again, 3.93, okay? So it's going to give you different numbers. Your numbers on your computers are going to look the same as mine, okay? Random stuff. So now I need to repeat this 10 times, and I need to store the sample means in an array. Okay, so you can do this with a for loop. Okay, we can do for I in range from 1 to the number of samples, get the sample, compute the sample mean, store the sample mean in a sample means array, and then plot that. So we can do this. And then I'll show you another trick that is much cleaner. Okay, so method 1. Okay, so draw samples. So now we're going to do draw num samples and compute their means, right? So for I in range is just a counter. I'm doing from 1. I'm going to do 10 samples. Why did I go to 11? If you're in doubt, print it out. So what is for I in range from 1 to 11? Print I. It's going to go from 1 to 10. So the high number is excluded. Okay, so I'm going to need to do, to num samples plus 1. Okay? So that's going to give me exactly num samples. Now draw a single sample for each I, calculate the sample mean, and I'm going to store the sample means in an array. Sample means is an empty list. Okay? And then I'm going to say sample means dot append sample mean. So what I'm doing here, like we did typical Python stuff, I created an empty list here. Once I'm getting to compute the samples, I'm going to go first sample, I drew it, I computed the mean. I'm going to take that mean and append it to the end of this array of sample means. When I do this with 10 means, I should have 10 sample means in this array called sample means. So let's print that. So if I run this, and then let's print sample means. Okay, I have 10 means. 1, 2, 3, 4, 5, 6, 7, 8, 9. Apparently I have 11. 10. What? Hold on. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Sorry, I counted this as this is part of the other one. Okay. There's a lot of numbers of the beast in here, like a lot of 6, 6, 6, 6, 6, 6, 6. Okay. All right. So this is fine. We can do this. And next, the last step is to plot those sample means. What are you going to do? A histogram. Okay. So we're done. Let's go ahead and plot that. plt.histogram. Sample means. I decided not to show you the faster method. I think it will just complicate things. Let's not do that. Histogram of sample means. Okay. And now my bins. So in my sample means, all right, let's do our bins is equal to actually something similar to this. Right? Exactly this. Now I'm looking at the distribution of sample means, and all right. Do you think it's going to work? Uh-oh. No, it didn't work. Okay, so let's try sample means. Let's try 10 bins. Hold on. Okay, it didn't work. My sample means. Okay, so let's draw now. Okay, let me go back here. Let's draw 1,000 samples. Okay, it's still giving me that one. Okay, instead of count, I think what we're missing here is that the y-axis is so large, we're not seeing any values here. So I need to convert this to a density. In other words, a frequency, relative frequency. So density, if I put density equal true over here, okay, that's still not giving me the answer. Okay, let's see, where did we make a mistake? We have 1,000 sample means, and the sample size is, did I overwrite something? Did I overwrite something? Let's see. Let's do 10 bins. Hold on a sec. Ah, there you go. Okay. Okay. So, yes. So let's go back to 10, just 10 samples. And here, just put 10 bins. Okay. Let it decide where it wants to bin things. Okay. And if you run this with 10 samples, you're not going to get much statistics. Okay. And there's a reason for that. Because this is going to be only true when the number of samples approaches infinity. Okay? But then we're not going to do an infinite number of samples in practice, because this is going to be true for any real situation. Here we're just trying to demonstrate that theorem, that theory. So I need to get close to infinity to try to demonstrate it for you. So if I take 1,000 samples, okay, you start seeing a bell curve show up here. Okay, if I take 40 in my sample size, you start seeing that distribution of sample means starting to show up. Okay, that distribution of sample means. Now, I want to overlay on top of this a normal distribution, but we don't know how to do it yet, because that normal distribution, those sample means, are going to have a standard deviation and a certain mean value. We don't know what those are yet. Okay? Anyway, so this is just trying to demonstrate to you what we are going to call the central limit theorem. That in the limit, as the number of samples approaches infinity, the sample means are going to follow a normal distribution. And you can keep pushing this to larger and larger samples, like 5,000 samples. You'll see that distribution emerge cleaner and cleaner. You can put in more bins, let's say 20 bins, for example, and you can see that normal distribution emerge better and better. Okay? All right, so I hope this was a little helpful. We're going to come back to this notebook, so keep it open as we're going to do an unfair die. All right, let's do some definitions now. We have, what, 8 minutes? Okay, a random sample from a finite population has size lowercase n from population. A finite population has capital size N. It's simply a set of observations whose values are chosen so that each subset of size n has the same probability of being selected. So this is the example with the die rolls. We have 300 population of 300, and we're sampling 40 or 30. Each one of those subsets has an equal likelihood of being chosen. That's a random sample, okay, from a finite population. Something a little bit more intense occurs with an infinite population, which is, we rarely we will deal with that on certain assumptions, but in the case of an infinite population, any set of observations constitutes a random sample if each one of those random variables that you've chosen is a random variable whose distribution is the same probability as the population. So suppose you have an infinite population of stars in the universe, right? The likelihood of the luminosity of a certain star, the PDF, the probability density distribution of that. If you pick a random star that from that population, that star is going to obey that same PDF. And also these n random variables are independent of each other. Okay, so that tells you you're going to do a replacement. Okay, so we're not going to influence the next choice by the first choice or the previous choice. Okay. More definitions. A statistic, remember in the first few lectures, a statistic is nothing more than a property or an observation, is any function of the observations in the random sample. So it could be the mean. The mean is a statistic of a sample, and on the population as well. So for the population, we call it a property. For the sample, we call it a statistic. The mean, the variance, the standard deviation, the expected value of some h of x, those are all statistics of a sample. All right? Okay, here's where we start getting into inference. Sampling distribution. The probability or frequency distribution of a statistic, so it could be mean. We just did the mean. We just did the distribution of the means. We could do the distribution of the variances. We could do the distribution of some other expected value. That frequency distribution of any statistic is called a sampling distribution. So we will use words like the sampling distribution of the sample means, the sampling distribution of the sample variances, the sampling distribution of the sample kurtosis, the sampling distribution of this or that. What does that mean? It immediately think of a histogram plot or a frequency plot of those means or variances. On the x-axis, you have the means or the variances or whatever other statistic you're looking at. On the y-axis, you have the frequency. Okay? So we're looking at the probability distribution of the statistic from the samples, not the population. Now, in this chapter, we're going from population to sample. In the next chapter, we're going to go from sample to population, right? Okay. Finally, the sampling distribution of sample means, okay, now be careful here, back to this definition, the general sampling distribution definition. It's the distribution across all possible samples. So if we wanted to do this precisely in Python, we have to count the number of samples that we could draw from the bag of 300 die faces, okay? From 300 die faces with replacement. So that's going to be a very, very large number, okay? So if you do that for all of those samples, few trillions of them, then, that's called the sampling distribution. Okay. Now, sampling distribution of sample means, the mean is simply a statistic for a sample. So the sampling distribution of the sample means is simply that plot that I showed you earlier. It's the frequency distribution or the probability of getting any one of those sample means. Okay. Finally, we hit the central limit theorem, which says that for any given population, finite or infinite, and this you can hold true. okay, for any given population, finite or infinite, and you know the mean and standard deviation sigma, okay, the shape of the sampling distribution of sample means, so now we're looking at the probability of sample means, the probability distribution of sample means, will approach that of a normal distribution as the sample size approaches infinity. The distribution of sample means is a normal distribution, and we denote that by x bar. It has its own mean value and its own standard deviation. Now, the nice thing is that the mean value of the sampling distribution of sample means, or the mean value of those sample means, is equal to the mean value of the original population. So for the die roll, Aaron kind of knocked it out of the park there. He knew that, right? So if you think about it, yeah, that should be true because we're taking the mean of means. It's going to be the mean of that population. In our sample means for the die, the mean value of the die is 3.5. You see, everything is centered at that 3.5 value. So indeed, the sample means are going to have a mean value of the population. Okay? So what that tells you, if you pick a sample and compute its mean, it's going to tell you the mean value of the population. But the standard deviation of the sample means is going to be the standard deviation of the population divided by the square root of the size of the sample. Okay? What this means is that, let me see, maybe that's going to be the question on the next slide. Okay. In practice, a sample size is large enough, is B large enough. Is large enough, is considered to be large enough if n is greater than or equal to 30. So there goes your question. How many subjects do you need to draw to be able to apply this theorem? 30 and large. Question? Doesn't matter. Because as long as you take more samples, what's really important is also the number of samples as well to prove this. But in practice, we're only drawing a number of a limited size sample. So yeah, it doesn't matter if your original population is infinite. Okay? So as long as n is greater than or equal to 30, it's a common practice. Now, the larger the sample size, the better the normal distribution approximation will be. Now, but you have to make sure that it's a random sample. So the challenge with a population of 10,000 is that with a sample of size 30, you're hardly doing a random sample. Really? Does that make sense? So as long as your sample is truly random, you're sampling from all districts, from all populations, ethnicities, genders, whatever, right? So that is going to bound you. But if you're greater than 30, yeah, that's great, as long as you touch on everything, right? Get all possible randomness as you can. Okay. So now I want to check this in Python. I want to check that the mean value of my sampling distribution of sample means, so the mean value of the sample means is equal to the mean value of the original population, or close to it, because we haven't done an infinite number of samples, obviously, and the standard deviation. So let's go and verify this in Python. Again, this Python exercise is a demonstration of this theorem. Okay, I'm out of time.